In this video, I'm going to be doing the implementation for the coin change problem. In the previous video, I went over the approach that we're going to use, and I've been solving a bunch of these dynamic programming problems, so if you're having trouble with this one, check out the playlist in the description. And what we're going to do in this video is we're going to start by writing the recursive brute force solution that shows how to break the problem down into subproblems, and then we're going to convert it to a bottom-up dynamic programming solution. And then we're going to try to reduce the space complexity to come upon the optimal solution to this problem. For the top-down solution, remember all we have to do is loop over the coins, and then for each coin denomination, we essentially take that coin as part of the solution, part of the coins that we're going to use to add up to the target value. So we subtract that coin's value off of the target, and we make that recursive call. And we do that for each coin, just keeping track of what the minimum is of all the recursive calls. And then we return that minimum value plus 1. The plus 1's because we're taking that one coin in addition to whatever the result is for the rest of the value. And because this is a recursive solution for the base case, we just have to make sure that we're returning 0 when we're trying to sum up to a value of 0. And if it's a negative value that it wants, then we just return infinity. It kind of makes sense to use infinity for invalid values when we're trying to minimize over things. That way you don't have to add in explicit checks. I know that the leak code question asks for -1 for invalid values. So what you can do is you can just add another function at the very top that makes this function call. And then if it returns 0, or if it returns infinity, then you just return -1 instead. So following the method I've been using so far, we then introduce caching to the recursive solution. All we have to do is initialize a cache, and then we add an extra parameter for passing the cache, and then we return directly out of it with the target value. And then all we have to do is add a check at the top to see if we've already solved the problem, and before we return a result, we just push the value into the stack. And this will reduce the overlap of the subproblems. But one thing to point out is that if we have a coin denomination of 1, then we're going to be making at least target number of recursive calls. So you can imagine that being like, at first it will call target -1 because we have to subtract the coin of 1 off of it. And then it will just keep doing that, target -1, target -2, all the way down to 0. And so if you have a large target value, you're going to be using a large number of recursive calls, which can be a problem. And so the next step is to convert this to a bottom-up solution. For the bottom-up solution, we start by initializing a DP cache, and it's going to have a row for each coin denomination, and it's going to have a column for each value from 0 up to the target, which I remember being kind of surprising the first time I saw it. It's just because when you make the recursive calls, essentially, we're subtracting each coin denomination off of the target value. So we actually need 0 all the way up to the target. And we initialize it with infinity because we're minimizing over values. It just makes it easier that way. And we start by setting the base cases, which is whenever the target's 0, we want a value of 0 in there because it takes 0 coins to reach a value of 0. And for these two-dimensional DP problems, I usually like solving the first row by itself before even attempting the problem, because it kind of gives you some indication of what the logic in the actual loop's going to look like, because the row is sort of independent of any of the other rows, because the row above would be an invalid value. And so for the first row, that's kind of like asking the minimum number of ways to reach a target value given only a single denomination. So all the values are just going to be multiples of the coin. And so we just loop through from 1 to the target value, and we just subtract the coin's denomination off and minimize over these values. It'll just be infinity if it's infinity plus 1. And so we have the first row filled in and the first column filled in, and then we get to the actual logic of the problem. And basically, so we're looping through each coin and we're looping through each target value, and the result for each cell then is going to be either from the row above. That's kind of like as if we're not using the coin at all in the the solution for the cell, or if the coin's value is less than the target that we're looking at, then we can see if we can use the coin by just subtracting that coin's value off and looking up the value in the grid and adding 1 to it. And so this is basically the same logic as the recursive solution, except now we're just doing it in a two-dimensional bottom-up way. And then we just return the value out of the bottom right part of the grid. And so when you look at this solution when it's printed out, I've printed out 2 examples here. And this is the DP when it's all filled in. So each cell is just going to be either the minimum of the value directly above it, or the as if we used this coin. So for this problem, the third row is a denomination of 5. So we have to look at 5 cells before it. So that'd be here. Plus 1 is 3. So the minimum of 3 and 6 is 3. So that's why this value is here. And it's like that for each value in the cell. And one thing to point out I think is kind of interesting is we can invert the order of these for loops, and it doesn't change anything about the problem. So that's kind of worth pointing out because there's sort of 2 different interpretations for it. It's either like we're checking each coin denomination, or we're kind of building it up row by row. And so I guess the next thing we need to do is convert this so that we're using less space, because for each cell, whenever we're only checking one previous row and a value that's directly to the left, then you know that we can do the same thing, just reusing the values. But for understanding the problem, I usually like starting off with a two-dimensional grid, because at least that way you can sort of debug and see if where your logic's wrong, if you have any invalid values in here and stuff like that. So to finish off this problem, we just need to reduce the size of the DP cache, and essentially we're just going to reuse all the same logic, but we're going to be overwriting values within a single row instead of looking up in the grid, which actually makes the code, I think, a lot easier to read, but if something goes wrong, it makes it a little bit more complicated to figure out why things are going wrong. And so all we have to do is initialize the cache. It's just a single array now with values of infinity. Set the base case to 0, and then loop through the values from 0 up to the target, and for each coin denomination. And then we just minimize over the value that's already been computed. And if we use that coin, we subtract that off of the target and add 1 to it. So it's the same logic as before. And then we just return out of the cache the last value. And so here's the output for this. And I think the only thing that's interesting to point out about this is, again, you can change the order of the for loops. And so the way we're doing it now is we're building it up basically index by index through the array. And for each index, we then do an inner loop checking each coin denomination. And we could do it another way. When you change the order, you basically build up a full array of values as if the problem was only for a single coin denomination, and then you add in another coin, and you build it up again, and then you add in another coin. And so I think that's just interesting to point out, because when you have a function like this and it has 2 parameters, it's kind of like there's 2 different dimensions that you can reduce the problem into subproblems by. So for this problem, you can either look at smaller target values, or you can consider what the problem would be if you had 1 less coin denomination. And so I think that's kind of interesting and something you can apply to more difficult problems.